Dear friends, do you know what is bonding? Yes, bonding is nothing but formation of a close relationship through constant association. Like this, there is a strong binding between metal and ligands. In this module, we are going to discuss crystal field theory, which reveals the bonding nature of coordination compounds. Bonding in coordination compounds are explained by various theories. Werner, the father of coordination chemistry, was the first to discuss the bonding features of coordination compounds. There are many theories which can explain the nature of bonding as well as various properties of coordination compounds. They are valence bond theory, crystal field theory, ligand field theory, and molecular orbital theory. Here we are going to discuss crystal field theory in detail. Crystal field theory is a bonding model that explains many important properties of transition metal complexes, including their color, magnetism, structure, stability, and reactivity. Crystal field theory was proposed by Hans Bethe and Van Velde. This theory gives much more satisfactory explanation for the bonding and properties of metal complexes than the valence bond theory. Crystal field theory is based on certain assumptions. The interaction between the metal ion and the ligand is purely electrostatic. That is, the metal ligand bonds are 100% ionic in nature. Negative ligands are treated as point charges and neutral ligands are treated as dipoles. Thus, the bonding in metal complexes may be ion-ion interaction or ion-dipole interaction. The 5d orbitals in an isolated gaseous metal atom or ion are degenerate, that is, they all have the same energy. However, when the ligands approach the metal ion to form a complex, the electrons in the d orbitals of the metal will be repelled by the negative charge or lone pair of electrons on the ligands due to the repulsion between the like charges. As a result, the energy of the d orbitals increases and the degeneracy of the d orbitals is lifted. It results in the splitting of d orbitals. The pattern of splitting of d orbitals depends on number of ligands and their arrangement around the central metal atom or ion. Let's look at the application of crystal field theory to octahedral complexes. In octahedral complexes, the metal ion is at the center of the octahedron and the 6 ligands lie at the 6 corners of the octahedron along the 3 axes X, Y, and Z as shown here. The approach of the ligands toward the central metal ion is considered a 2-step process. In the first step, it is assumed that the ligands approach the metal ion spherically, that is, at the same distance from each d orbitals. At this stage, the energy of all the d orbitals is raised by the same amount. That is, the 5d orbitals still remain in degenerate state. The average value of energy of 5d orbitals at this stage is taken as 0. This is called the Barry center. However, out of the 5d orbitals, 2 orbitals, that is dx squared minus y squared and dz squared orbitals, which are collectively known as Eg set of orbitals, are oriented along the axis towards the direction of the ligand. Thus, Eg set of orbitals will experience more repulsion than the Remaining 3 d orbitals, that is dxy, dxz and dyz, which lie in between the axes. These 3 d orbitals are collectively known as T2g set of orbitals. Consequently, the energy of Eg set of orbitals increases while that of T2g orbitals decreases relative to the average energy in the spherical crystal field. Thus, under the influence of the ligands, the degeneracy of the 5d orbitals of the metal ion is lost, and they are split into two groups of different energies. This effect is known as crystal field splitting. The extent of splitting is represented by the symbol delta O. The subscript O indicates octahedral geometry. Due to the splitting, the energy of the 2 Eg set of orbitals will increase by 3/5 of delta O, while that of 3 T2g set of orbitals will decrease by 2/5 of delta O. The magnitude of crystal field splitting depends upon the field strength of the ligand and the charge on the metal ion. Ligands that cause only a small degree of crystal field splitting are termed as weak field ligands, while the ligands that cause large splitting are termed as strong field ligands. In general, the common ligands can be arranged in descending order of field strength as shown here. The order remains practically constant for different metals. This series is called spectrochemical series. Now you have understood what is crystal field theory and its application in octahedral geometry. This video will help you to differentiate weak field and strong field ligands in crystal field splitting. Thank you.